Welcome to our first developer community meeting of the year. It's actually January 31st, 2023. Today, we'll be providing a high-level overview of just some community updates and what we've recently released on the ML and the SDK side. But we're going to quickly jump into our guest presentation, which will be Luke here will be presenting his research. We're very excited to hear more about that. So just a couple refreshers. We do have this community meeting that we host just about every month. We are going to be having guest lectures occur more often. So if there are topics that you're interested in us presenting, please email us at developer@cerebras.net. Additionally, there is a discourse page that we do host. There's a lot of great conversations, a lot of good Q&A that happen there. So if you haven't signed up already, or if you're interested, please join discourse.cerebras.net.
Uday, I'd like to point out real quick that actually one of the most active conversations going on in discourse the past couple weeks has been working out a pretty interesting solution to one of Luke's problems.
Yeah.
So yeah, please, if you're using the SDK, please join.
Yeah, and if you're on the discourse page and you're wondering, who this Luke guy is that keeps asking really tough and challenging questions, well, you get to meet him today. So, all right, let's jump into what's new. So, we've had a couple launches since our last community meeting. I'll spend some time talking about the ML software launch, and Leighton can talk about the SDK. But from the ML perspective, we now provide computer vision support. So we provide support for 2D segmentation with UNet. The interesting thing here is that we support images up to 5K by 5K without tiling. So as you can see in the image, obviously having 5K by 5K provides a level of crisp and granularity that you might not be able to achieve otherwise. On the PyTorch support side, we now support GPT-J and GPT-3 models up to 20 billion parameters. We have also done some work internally to improve the performance of these models by about 1.5x. And finally, and this is interesting, really interesting to us, that we do now support training with sparse weights in PyTorch. So, there's a way to convert dense PyTorch checkpoints into sparse versions now, and this is a kind of a new offering that we're giving to our ML community. So with that said, I'll hand it over to Leighton. Leighton, you can introduce the SDK.
Thanks. Yeah, go on to the next slide. Okay, so I want to take a second just to back up. I know, we often have members joining who are much more familiar with our ML stack. And so it might be helpful to get everyone on the same page with what exactly we can do with our SDK and how to think about what we're doing. So I'm sure everyone in here is at least vaguely familiar with our architecture. We have about 850,000 general purpose cores laid out in a regular grid. The strategy that the SDK uses for programming this gigantic grid is data flow programming. So there are tasks on each of your processing elements, and they're activated or triggered by the arrival of data packets. These data packets we call wavelets. So that's the data being shuffled between these processing elements. And the routes that a given wavelet takes, we call colors. And these routes can be static, or they can actually be dynamically changed at runtime. But the important piece there is that when we talk about colors, we're talking about routing between our processing elements. And when we talk about wavelets, we're talking about the data packets that we send between our processing elements. Also important to note that the way our memory architecture works is that each one of these processing elements has 48 kilobytes of SRAM on it with a single cycle to read or write. In fact, in certain circumstances, you can actually do 2 reads and 1 write all in 1 cycle for a 32-bit chunk of data. And then sending messages between our processing elements also only takes a cycle, sending to your 4 neighbors. Okay, next. Okay, so the SDK, what do we provide? Well, it's built around CSL, the Cerebras Software Language, which is what Luke has been using in all of his work. It's a C-like language. It definitely has C heritage, but with a lot of other stuff built on top for the purpose of actually meeting the unique challenges of programming this wafer. We have host APIs that are in Python currently, with C++ support coming in the future. Whole bunch of libraries, optimized primitives. These are constantly growing and evolving. And on the tools side, we have a debugger and a visualizer tool in particular, which you see on the right here, and our simulator, which allows you to actually do a lot of development, not even on an actual CS2 system, but just on your desktop computer. So from a programmer's perspective, the way this works is we have host code that's written in Python that loads the program onto the simulator, the CS2, streams in and out data, reads and writes the device memory. And on the device, we actually have our CSL code running, which again could be in a simulator or a real CS2. And this code executes data flow programs, and these programs run on groups of cores on the wafer specified by the programmer. It could be the entire wafer. So just real quick about the language. It should be generally familiar to C, C++, HPC programmers. We take a lot of things straight from C via a language called Zig, but I mean, everything you would expect in a modern language. Certainly a much nicer and friendlier type system than C. And then a bunch of CSL specific things that really allow you to get the most performance possible out of the wafer. So our current release has a new runtime with a high bandwidth memory IO API. So what this means is that we can stream data on and off the wafer using CSL programs at about, we can reach roughly 12x what we could before. This new runtime is still in its early days, and the documentation is still working its way. But we're really excited about this and hope with the 0.7 release, we will more prominently feature the work on this new runtime. We also have some new communication primitives. So these allow you to do slightly more MPI-like programming, to do like a gather or a scatter along a row or a column of PEs. So this is also a big focus area for us to target and keep developing to kind of expose a more MPI-like method of programming all these cores. We also have support for remote procedure calls, and this goes with our new runtime. Of course, our ongoing work is always new libraries, robustness, stability, making our user experience as good as possible. I'd also like to point out that we have work going on along the new runtime to start allowing users to write C and C++ host code. So I think this is also very exciting. So let's hand it over to Luke.
Right. Can you stop your screen share, please?
Yep.
Yeah. Right. Can everyone see that?
Looks good.
Okay. So the plan for this presentation is as follows. We first motivate graph algorithms, look at graph algorithms and all the different kinds we have. Then we go over to the Graph500 benchmark, and we introduce our approach that we use to run this benchmark. And in the end, we will look at tooling and how this tooling supported us in building this implementation. So if I could take a guess, I would say that everyone has used a routing app in the last week at least once to get from one path to another, from one place, go from one place to another. If I could take a second guess, I would also say that this routing app probably employed a graph algorithm to help you to get this good solution. And this is not by chance. Graphs are a naturally arising structure. They can expressively model relations between multiple entities, and thus it's quite easy to express real-world problems through these graphs. And a large part of computer science uses graph algorithms to solve problems. For example, let's take ships, containers, and routes. They can be expressed in a network in which we can optimize these routes and how the containers are placed on different routes to minimize costs and make the transport more efficient. Another example we have are bioinformatic pipelines. They make heavy use of graph algorithms, especially in genome and metagenome assembly pipelines. There are other examples, for example, in financial services, online social networks, recommender systems, lots of things basically can be modeled as graph algorithms. The problem is we have a lot of graph algorithms, and now we want to figure out how to efficiently run them, maybe on a Cerebras wafer scale engine. So let's look at one graph algorithm, a very simple one. So let's take breadth first search, or short BFS. It is probably one of the most fundamental graph algorithms and a very simple one. So we are given a graph and we're given a starting node. And now, level by level, the goal is to, for a parent, explore all of their children. And we do this repeatedly until we have traversed the whole graph. Now, as I already said, there are lots of graph algorithms. Luckily, a lot of graph algorithms tend to use some sort of BFS or use the same requirements as BFS or rely upon the same principles. So we can say by looking at BFS, we have quite a good representative of the group of graph algorithms. And the Graph500 benchmark gives us a framework to evaluate the performance of running BFS and compare them to other systems. Currently, the Fugaku is probably the fastest system, but it's probably quite difficult to scale. And we will look at that a bit more in detail. But for now, to compare this benchmark to a even more traditional benchmark, the top 500 benchmark, where we measure the floating point operations per second. Here we measure the traversed edges per second, so how fast we can iterate through this graph. For the top 500, we have an input which is represented as a dense matrix, and the graph for the Graph500 benchmark is a sparse matrix. And yeah, we solve a linear system, and in our case, we find paths and through BFS. So the interesting thing about this top 500 benchmark is that it almost scales linearly with added nodes. We don't really care much, or communication is not really important. While for the Graph500 benchmark, communication is quite important. That is probably also why the Fugaku is so good. And from back of the envelope calculation, we see that we only use 1% of the available operations that are given through the system. However, for the top 500 benchmark, we can see utilizations up to 99%, which is very high. So you get quite a fast system, but you can only use 1%, and that's kind of a bummer. So looking at the Fugaku, it has roughly 100,000, I think maybe 104,000 nodes in this benchmark, but we only get 1,000 times the performance of a single device. That's quite disappointing. Well, it's very good. It's the best they could do, and they are very capable. However, the scaling is very, very difficult. It's very difficult to scale this benchmark. Excuse me. And what we can say is that adding nodes seems to be not as efficient. However, what about having bigger nodes? So what about vertical scaling? And this is what we try to do here. We try to map a non-machine learning workload onto the CS2. And we believe that through doing this, we have an indicative benchmark of how other graph algorithms might also perform. So just by doing BFS, we can see how well might other graph algorithms perform. And we think the CS2 might be quite well suited, as the BFS benchmark cares about how much latency is in the system. That is memory latency, communication latency, how much communication can we do. And the CS2 has quite good numbers on the paper. So we have a very high memory bandwidth. We have one cycle for load that is incredibly fast. And the fabric latency is also quite low. So from one side to one side of the chip, we have 1 microsecond of one edge to one edge time. So we already talked about the mental model, but I just wanted to stress this again. The chip itself is placed in a 2-dimensional grid where we can only do peer-to-peer communication. So doing completely global random communication, especially when we have a graph which is very irregular, this is quite difficult because we have to communicate over all of these jumps. We don't really have a centralized network or some more advanced network topology. So we have to do this peer-to-peer communication. And now we want to reformulate our BFS run to have a more regular structure so that it somehow fits onto this chip. And what we do is we can reformulate BFS as a sparse matrix, sparse vector problem to then represent the iteration the BFS algorithm takes. So what you can see here is a graph that we represented in a sparse matrix. And you can see the current time step, which is this start node 1. And you can see the next time step, xt plus 1, indicated as the yellow vector. And when we multiply it, we get the next time step. And looking at how data flows here, we can see that the current time step gets broadcasted along the columns. And then we reduce the results along the rows, and we call this the fold phase. So it's the communication patterns here are quite regular. So we have placed this this irregular data structure into quite regular one. And now we map this onto the single processing elements of our wafer scale engine. And here represented as yellow is the matrix where we do the small matrix multiply, and we regularly 2-dimensionally block distributed this matrix. And the current time step xt, you can see at the top, it broadcasts its information down, and then it generates some data, and then it folds into the right. However, if we want to do this repeatedly, we have to move the data from the right blue block to the top blue blocks. And that is quite inefficient. So we want to find a way to store our level information more efficiently. And we do this by placing it at the intersection of fold and expand phase. And when we do this repeatedly, we can see that the state now lives on the diagonal of the wafer. And now the goal is to implement this. So this was our initial approach. Place the data on the diagonal and then do from this data, broadcast the data outwards in the columns, and then reduce it along the rows into the diagonals and build the next state, which we then send out again. And we do this repeatedly. So let's look at the high-level workflow of how we approach this. We start by mapping single code files to each PE on this PE grid, on this wafer scale engine. And this is a bit different to what MPI usually does, where we run the same program everywhere. Here, we place a different program onto each onto each tile or onto each PE. And we have to configure our network, and then the compiler spits out a bunch of ELF binaries. We then go over to Python, and this is more of a development flow thing, but we modify these ELF binaries, and we change some data that's behind some symbols to preload some data, because we don't want to write upload and download programs. This is just to speed up development. And then we can either run it on a simulator, and we want to run it on a simulator for as long as possible to get some more signals out of the simulator. And when we are ready, we can upload it to a different machine and then run it on an actual wafer scale engine. So that's the general workflow. And now we've built a small tool library around this to help us a bit with debugging and visualization around this workflow. So in general, the library is called Sprint, and it's an ad hoc drop-in which you can just launch in your Python shell, or you can use it as a separate program to run on your ELF binaries and your simulation traces. So it's quite simple to use, and it offers debugging utilities for when you have problems. But for now, we will look a bit into the profiling utilities. And then also some additional stuff. I'm not a Fortran person, so I'm more used to the row major accessing of data rather than the column major addressing, but that's maybe just a thing that's on me. So let's use the first tool to look further into how our approach does. The first thing we have is a profile report. So we want to look at how code runs on a single PE, on a single processing element. So we just look at this one element, and then we collect some high-level statistics. So a wavelet comes in, triggers a task, and now we want to know, well, how long does this task usually run? And so on. And we have some more, and then when you want to drill down, we have some more in-depth statistics for line-by-line profile of each of these tasks. And as you can see here in our approach, when looking at this PE, we have this activation task, which accepts the broadcast, and then we have a forward task, which is responsible for the reduction, for the forward phase. So when we look at the output of our profile generator, we can see that the activation task only takes 44% of the runtime, which is not necessarily good, because that means we spend more than 50% on the forwarding task. And the forwarding task should actually not be that difficult, because we do a final reduction in these diagonal tiles. So that doesn't really, well, look good. We have 400 calls to this task, so we receive 400 data packets and then call a function on call this task on that. We also plot the most traversed times. So when we run the main thread and we just run a single program and we don't have communication, the hardware is quite deterministic, so we can see the code paths represented in these times. So we see that 92 times we had a runtime of 20 cycles, and then we can see when we do the line-by-line report roughly where our data path and was on the processor. And we have a we show a histogram, so we can roughly see the where the density is and where in which area or which group is most often represented in this runtime. And now when we drill down into the forward task, we can see that this forward task was called 5,600 times, which is quite a lot. And for example, this line took 21% of the runtime, and then the next line roughly takes 31.9% of the runtime. So that combined is over 50%, which is a lot. And the fabric actually can do all of the routing. So we don't have to pull it back into the PE, do some processing on it, and then push the data out again. So this is the first thing we changed. Instead of doing all of the processing on a PE, we now introduce PEs, which are solely responsible for merging all of these different colors that a wavelet can arrive on, and then bundling it into a new color and forwarding that into the next merging PE. And this is what it looks like. So the wafer is actually not really square shaped, but it's a bit rectangular. So we can just introduce some columns which are only bundling colors, and so we don't have to do it on the yellow PEs. So that's one thing we can do. We can just look at the performance of a single PE. But now we want to understand our system a bit more holistically. We want to understand how these different code pieces are interacting with each other. Where's the bottleneck? And to figure that out, we have to look at a concept called backpressure. Backpressure, so as we already said, we have a data flow architecture. Everything is triggered when data arrives at a processing element. And what happens when a processing element is busy? For example, we still do some computation and we cannot really receive any more data. The wavelet is backpressured. So it stalls, it doesn't arrive in the PE, and it's not sent from the previous PE, and then backpressure propagates back to the origin blocking to the origin of these wavelets. So it first starts where we have a bottleneck. So this is the processing PE. And for that, we have the second tool to now analyze our new approach. And we want to visualize backpressure and understand how multiple PEs can work together. And this can be done, for example, through wavelet throughput, to wavelet delays, latencies, and we maybe also want to visualize this only at a certain time range. For example, we know our algorithm at a certain cycle is at a certain point of an algorithm, and we now want to understand only during this part where is backpressure created, where is data not processed. And this would be an example of how to use it. So we can generate a backpressure report. We can just use all colors used. We can only use specific colors, and we can define a start and end range. So it's quite a simple API. And this is what a backpressure report would look like. So this is a combined report. This includes multiple colors. And the overarching picture, what you can see is there's not much we don't see much backpressure in the diagonal. However, backpressure is only created in front of a busy PE. So we see that because the diagonal here is not really busy, we see that data going into the diagonal is blocked. That means that the diagonal takes too much time, and this is why backpressure is building around that diagonal. We can also drill down a bit and just look at specific colors and occurrences of backpressure. And here I've taken the color that is directly connected to those diagonal tiles, to those diagonal PEs. And this is backpressure in % of runtime. So how much % of the runtime are we backpressured? And we can see it's roughly up to 40–50%. And I placed the diagonal PEs here just to visualize it more clearly. And we can see the longer the row is, the more backpressure builds. So that correlates with what we expected to see here if the diagonal PEs are slow. And because of that, because now we know that the diagonal is kind of a problem because we're storing data there, we are also doing some expansion, we're doing a lot of work. Those PEs are too busy. Also, they have to receive all of the data coming along the rows and merge them there. So what we do now, and this is where we depart a bit from what we will later explain in our manuscript, we add more complexity to the system. This is mainly introduced through parallelizing the different steps that happen in these diagonal PEs. And we do a lot of work to then also parallelize the data that comes in and pull out the PEs, introduce different functionality. And this makes it, well, we're slowly building kind of a complex system. And things we noted during development are that placement can become quite error prone, because now you need to place functionality and parameters onto a specific spot of this grid. And you have some problems like off by one errors and stuff, where now the placement, if you mix up some things, you have disconnected functionality and things don't work. So we want to have something that checks if everything is in right order, and we want to have something that verifies that everything is connected properly, because not only do we have to place the code files with the functionality and assign it to each and every single PE, we also have to check that all the colors and the routes and everything is connected and properly set up. And the third tool we introduce is just it can print and show where you have mapped different code files and where to which position. And this again is different in the beginning to what you would see with MPI, because you would have only one program, but here it's really important which functionality lives where. What you can also do is then you can go into these single PEs and you can look which parameters and values you use to place them. And the fourth thing is focused around, so the fourth tool is focused around how we place and connect, how we connect these PEs. The PEs have outgoing and incoming routes, and you need to set up on two adjacent PEs that should communicate. You need to set up the transmitting side, and you need to set up the receiving side. So if both are set up, which you can see on the right, in this with indicated with the screen arrow, everything works properly. So your functionality set up. If you connected these colors internally to other parts, is not of our concern here. And what can happen now is that you set up a receiving side, but you have no transmitting side. We say here that's a warning, because maybe you just have a very simple setup and you don't really want to set up all of your routes to perfectly match each and every scenario. So you have one PE that, for example, can receive something from every direction, and not every direction is always connected, so that's totally fine. However, we have a problem if we only set up a transmitting side, and this gives this for us triggers a warning, because if you have no receiving side, the wavelets that are generated on the transmitting side, they are blocked, and then our whole code just stalls and does nothing anymore, and we are, well, in a deadlock scenario, which is really bad, because then we get wrong results and our simulation finishes preemptively. So because of this highly complex routing, usually the workflow is to open the debugging guy and GUI, and then use a tool, for example, CS-readelf, to verify the routing tables. And you really need to play around with, you often need to write down information and input it from one tool into another tool, and this is quite tedious. So what we've built is a small routing checkup doctor tool, where you can check for dead links and you can show these different levels. So for example, you can show warnings and you can only show errors. And this is an example of how we used it during the development, and this actually helps quite a lot to find errors while working with more complex code. So here in this example, you can see that we have set up a transmitting side, and the transmitting side is in position 6.1, sixth row first, no, six column first row. This is what I mean with, I'm not a Fortran person. And you have this on color number 2, and then you can see that the routing table only says, okay, we are connected to north, and the broken link is also the north link. So now we can jump into the code and want to introspect it more and figure out what actually happened. Why is it not properly set up? And for visually doing this and having this all within one system to quickly dive into the different configurations and our different PEs, we also have a small shell interactive debugger, which prints you very essential information for quickly figuring out what's happening here. So when we launch our dive, you can jump around with your keyboard up, down, left, right arrows. And you can see here, we first print the symbols. We show where is this PE located. We show which file it is associated with. So this is some information you previously have seen, but now it's within this tool, so you have it always available. And then we print after the simulation or before the simulation, depending on when you launch this tool. We print the memory and the values that are assigned to all the variables or all of your symbols in this L file. And you can also access this and work with it, write tests. We also print the size that the PE is occupying. We print some routing information here. We also, with a color, indicate if it's a warning or if it is an error. We show some common names. We show how many colors are used. This is really helpful. Also during normal development, when you want to figure out, okay, I've mapped these colors, these are still available. Sometimes this is, if you don't have proper color management and you really didn't have a system in the beginning, this is quite helpful to still spot which colors are available. And in the end, we also print a small summary of where this trace and where this debugging information was taken from. So the Sprint library is not open source yet, but we wanted to open source it. And those were not all the features that are presented. So there are more features, but they didn't really fit into this presentation. So we have a small auto formatter. It is a bit buggy, and it only works for 0.5.1. I didn't have time to fix it yet. We have some rotational APIs. So you can, when you define your kernel, you can just flip it around, transpose it, and everything is well then mapped in a transposed way. This is quite helpful. During development, sometimes you mix up the orientation, and instead of starting over, you can just transpose it, rotate it, and place it next to, for example, other kernels. Yeah, then we have more in-depth backpressure reports, instruction reports, some more debugging tools, smaller ones. We can also, instead of having this profile trace for a single PE, we can have a profile trace, an instruction trace, and a line-by-line trace. We can merge multiple PEs together to generate an average, and we can diff these against previous versions of the same file. So you can see when you've done something, how you have improved the performance. We plan to also hopefully be able to figure out how to deal with asynchronous operations because they're currently not accounted for. That's a bit difficult. I want to figure out how to tell someone if we stop the simulation because we ran into a deadlock. I want to figure out how to get behind blocked color states. You can block colors and unblock colors. And this is also something that I'm currently doing manually by setting values in my memory, indicating if I have a block color or unblock color. So ideally, I want to get this from the simulator. One thing that's a bit tricky is running unit tests, but I have some ideas of which I will include in this library. All in all, if you are interested in using this library, you can contact developer@cerebras.net, and they will notify me, and I will put you in the private GitHub repository. If you have ideas, if you are interested, if you have a specific workflow, let me know. I will try to include it. Just open an issue, it's kind of a formless issue. Just write what you're interested in, and I will try to address it. Coming to the paper and to the performance numbers, we will have, because we missed out on a lot of points here, we will have a more in-depth review of the performance numbers in a manuscript, which we will soon publish on arXiv. And once that is published on arXiv, it will also be published in the forums. So there you can get more performance numbers, and we have a more in-depth view of what approach we took to implement BFS, and how it later compares to other hardware. In general, we can say that, well, even though these graph algorithms are quite irregular, we have a chance to actually run them on the hardware. And maybe because we have a bigger hardware, we can get some good single device scaling numbers. Thank you very much for your attention. I think I used my 30 minutes, and I would hand it over to questions.
Yeah, Luke, you actually have a question in the chat. So Mia asks two questions. One regarding P39. Did you experience any performance difference between the real CS2 and the simulator? And then regarding P52, how do you get the size of the used memory?
Okay. So yes, we experienced some differences between the simulator and the actual hardware, and it goes both ways. But it's not necessarily for a single PE, but for more complex systems, because sometimes latencies can be slightly different on the real hardware. And this, because we have such a complex system which interlocks, and we have many components that that are working working together. If we are sometimes one cycle off, this means that, for example, another wavelet is received first, and then we get into a different state. However, the performance differences are marginal. It's a few thousand cycles of hundreds of thousands of cycles. So the performance difference is not large, although we get them. But for smaller runs, it's a bit more. But once we approach a certain size, it's almost not noticeable, or it won't be noticeable in the final benchmark numbers. The second question is, how do we get the size? What I do is page 39. Oh yeah, sorry, page 52. Sorry for not skipping to the one first. This one, yeah. So what we do is we look at all of the symbols in the F binary, and we sum up the sizes of all of the symbols.
Luke, I want to add something real quick on your first point, which that so Mia, who asked the question, actually undertook a really interesting investigation related to our memory bandwidth performance, and so your application is a good example of like a real world use case where you have like these DSD operations that are both doing lots of receives from the fabric and reading from memory. If you built an application that was just, say, doing a DSD operation over and over and over again, that was just reading from your memory on your PE, then you could begin to see a significant amount of power throttling on that individual tile. Because in terms of like the way that we handle power throttling, doing lots and lots and lots of reads from your local memory over and over and over again and no other operation can start to slow you down. It'll start putting in some empty cycles, which is something that Mia himself uncovered when he was doing some benchmarking. But in your case, right, you also have lots of these fabric sends and receives, which are significantly lighter on the hardware. And so when you have lots of fabric sends and receives at the same time that you're reading from your memory, you are much less likely to experience a performance difference between the simulator and a real CS2 because of power throttling.
So maybe one thing to mention is that the runtime is under the runtime is under a millisecond for benchmark run. So that's quite quick before power throttling, I think. But yeah, I've not looked into that.
Were there any other questions that we have from the community for Luke in his presentation today? Going once, going twice. All right, Luke, we can conclude then. Hey, thanks. Thank you so much for presenting today. This was very informative, and it's really exciting to see the work that you've done using our CSL and our SDK and soon to be a paper published on this research. Just as a reminder to the audience, Luke did provide notice that if you do want to engage with his work and his code, feel free to reach out to us at developer@cerebras.net. There you go. And you'd be able to get access to Sprint, which I think is a lot of really exciting and really great code in there. Yeah, that's it for today. Thanks again, Luke. Appreciate your presentation, and thank you all for joining. And we look forward to seeing you all next month.